I'm gonna explain Euler's identity, which is the most beautiful identity or most beautiful equation in the mathematical history. So to prove this, let me just say, how do you find phi to the power of 0.911, let's say. Now let me draw the graph of phi power x equals f of x. And the graph would look like this, and I'm gonna zoom right here as far as I could. So let me draw it in another page. When I zoom a lot, it just looks like a straight line right here. Yep. And now if I zoom in a lot, it looks like a straight line. So a general form of straight line is ax plus b. So where a is the slope of this line and b is the intercept. That means it's this length. So to find this length, we should find the value of phi to the x at x equals 0. So because here its x coordinate is 0, so if I put in 0, I get phi to the 0. So I can write it as phi to the a minus a, and that would be phi to the a divided by phi to the a. So I can cancel these both and I get 1. So we know that b equals 1. We know that b equals 1. Now to find a, we need to differentiate this function by using some basic calculus rules. We can find phi to the x times ln of phi, and that would be equals to, so we are zooming at the point where this x coordinate is 0, so phi to the 0 is 1, we just found it, and ln of phi. So now I used a calculator and found this value as 1.6094. Surely at that time there is no calculator didn't exist, so let me put a box around it so that this slope a equals 1.6094, and now we can write the equation, the straight line equation. 1 plus 1.6094 times x, right? But this only works for the small values of x, like 0.0000991. So now I have to find the value of phi to the 0.991, which I already told you, right? Now to find that, let me just first find the value of 0.0000991, which would be equal to phi to the 0.991 divided by 1000, so that this value is really small, so it works for this equation. If we put that value 0.0000991 equals 1 plus 1.6094 times 0.0000991, and that would be equals to, approximately equals to 1 point something. I don't know that something. If you want it, you can put it in a calculator. So now to find the value of phi to the phi power 0.991, I can just write phi power 0.0000991 whole to the 1000, and this part 1 point something whole power 1000. it's 1000 right here. I'm so sorry. Now the value of that would be, and we got that value. I don't know that value, you can put in calculator, but what we did is we just wrote that 5 to the x equals 1 plus 1.60494 times x, right? But we told that this only works for small values of x. So what I can do is I can write 5 power x by n approaches to infinity, and I can write that is equals to 1 plus 1.0094 times x divided by n. And to find the value of 5 power x, I can just write 5 power x divided by n whole to the n equals 1 plus 1.60994 by n and whole power n, and we can just cancel this both and we get 5 power x equals, we know that n approaches to infinity, so we can write a simple limit form. Limit n approaches to infinity 1 plus 1.6094 times x by n whole power n. So this is the value of 5 power x for not small values of x but for every values of x. So now we can change this we can change this base, and if we change this base, this value should change. So this is just an approximate value, not an actual value. So if this equals to 1, we can find the exact value of some function, like let's say I think e power x equals limit n approaching to infinity 1 plus, and this value would be 1 times x by n whole power n. So this e is nothing but Euler's number. So let me explain what e is. So as we did for 5 to the x, if we do to e to the x like this, and if we zoom a lot, we get e to the x equals 1, a plus bx, a general form of a line. So it must look like a line when we zoom a lot. So now we know that a equals 1 because e to the 0 equals 1. Now we can write e to the x equals 1 plus b to the x, b times x. Now the special part of this function is here the b value of b equals 1. So e to the x is equals 1 plus x. And that's what Euler found. He found a new constant called e, and he told, and this speciality of this function is, it's if you differentiate it, we get same e to the x. So if you differentiate it again, you're gonna get same value. So now we know that for small values of x, we can write 1 plus x. Now let me write like what I did to 5 to the x, e power x by n whole power n equals 1 plus n divided by x divided by n whole power n, and I can cancel this both out. So now here for every values of x, we can write e to the x equals limit x approaches to n approaches to infinity 1 plus x divided by n whole power n. And we just found the value of e power x everywhere. Let me just write it right in this page. And let's try, I'm gonna put it in a box so that I can use it later. Now if I quickly write two complex numbers like e power ai, and I'm gonna write the conjugate of this e power minus ai. The conjugate of this complex number is this. So if I quickly multiply it, I get e power 0, that is equals 1. So that for any values of a, we can take a is equals to 1000, a equals minus infinity, infinity. We get e to the 0 equals 1. So that these 2 points must lie on this unit circle, somewhere like this, right, or right here. So I can use some trigonometric knowledges and I can write e to the ai equals, this value must be, let me take this angle as theta, so cos theta, and this is sine theta, so it must be equals to cos theta plus I sine theta. And now I'm gonna find the value for e power I, e power 2i, e power 3i. I'm just gonna find the value for this. If you ask me how I'm gonna find the value for this, I'm gonna use this equation, which is e power x equals limit n approaches to infinity 1 plus x divided by n whole power n. And now if you put x equals I, 2i and 3i, I get e power I equals, let me just, 1, the, 1 and 57.296 degrees. This is called polar form. Let me just explain you what is a polar form means. So let me take a point right here. The angle is 45 and this length is 1. I mention it one length and 45 degrees. Now if I do it for e power 2i, and that is gonna be equals to 1 and 592 degrees. And for e power 3i, I get 171.887 degrees. And if I write these degrees in radians, I get e power I equals 1 and then 1 radian I get these values. So now if this are the theta right here, if I put e power ai equals cos theta plus I sine theta. Now for a equals 1 equals, I got 1 length and 1 radian. So cos of 1 radian, that means 57.296 degrees plus I sine of 57.296 degrees. So if I write for this e power 2i equals, that is cos of 114.592 degrees plus sine I sine of 114.592 degrees. So if I increase this A by unit 1, I'm increasing this angle by unit 57.296. So in radians this is 1. So if I increase A by unit 1, I increase the angle by unit 1 radian, and that's cool. So we just found the relation for A, and theta, so that A equals theta in radians generally. So e power I theta equals cos theta plus I sin theta. You know what? How cool is it? And if you enjoyed this video, don't forget to like and subscribe. Thank you.